Today we're trying to get into the most exclusive club in all of chemistry, the noble gases. Seriously, these elements are the true aristocrats of the periodic table. They're aloof, they're stable, and they are famously unwilling to mingle with the commoners. But why?
So what is it that makes these elements so special? So noble? Well, their secret lies in a kind of chemical perfection that makes them unbelievably stable. So in this explainer, we're going to pull back that velvet rope and find out exactly what that secret is.
Okay, so officially, we're talking about the elements you'll find in Group 18 of the periodic table. You might have also heard them called the inert gases. This is our VIP list for today.
All right, so who's on the guest list? We've got helium, from balloons, neon, the element that lights up our cities, then there's argon, krypton, and xenon, and rounding out the group is the radioactive one, radon. Each one is a bit different, but they all share one critical family trait.
So let's get right to the heart of it. Why are they so noble and unreactive? The answer has nothing to do with their social calendar. It's buried deep inside their atomic structure.
The whole secret comes down to their electrons. Think of it this way. Every atom has these shells of electrons, and an atom is at its most stable, you could say its happiest, when its outermost shell is completely full. It's just a lower, more comfortable energy state to be in. Well, the noble gases have already achieved this perfect balance. They have no need to gain, lose, or share electrons with anybody else. They are perfectly content all on their own.
And we can actually measure this stability with something called ionization energy. It's basically the price you'd have to pay in energy to snatch an electron away from an atom. And for the noble gases, let me tell you, that price is incredibly high. A high ionization energy means high stability. They really, really do not want to give up their electrons.
And you can see that reluctance visualized so clearly right here. In any given row of the periodic table, any period, the noble gas just towers over all the other elements. I mean, look at those peaks. It's a dead giveaway of just how chemically stable and content they are.
Now, even within the group itself, there are some pretty clear trends. As you go down the column from helium to radon, the atoms get bigger, their boiling points creep up, and, interestingly, it gets just a little bit easier to remove an electron. But helium is a real standout. Not only does it have the highest ionization energy in its period, but it also has the lowest boiling point of any element on the table. That's exactly why it's so critical for cryogenics, the science of extreme cold.
So for a long, long time, we called them the inert gases because everyone believed they were completely 100% unreactive. But, as scientists got more clever, they started to wonder, is this club really that exclusive? Is it possible we could actually persuade one of them to react?
And it turns out calling them inert was a bit of an overstatement. The story of the noble gases was about to get a whole lot more interesting.
So which ones are the exceptions? Well, meet xenon and krypton. Now, they're still very stable, don't get me wrong, but these are larger noble gases, which means their outermost electrons are way further from the pole of the nucleus. And that distance, that makes them just a little bit more vulnerable to the right kind of chemical persuasion.
Let's focus on xenon, because it's the prime example that completely shattered the myth of total inertness. It was the very first noble gas to be coaxed into forming a stable chemical compound.
So how'd they do it? You need an extremely persuasive dance partner. And for that, you bring in fluorine, the most electronegative element there is. It's the ultimate electron thief. Under just the right conditions, with high temperature and pressure, fluorine can actually convince xenon to share its precious electrons, forming compounds like xenon difluoride. The exclusive club had finally let someone in. And this wasn't just a one-time thing either. Since then, scientists have created a whole range of stable xenon compounds. Just look at the variety here. They form all these different complex geometric shapes. The point is, xenon can actually participate in some surprisingly sophisticated chemistry. The myth of total inertness was officially busted.
So, we've peeked behind the curtain at their secret stability, and we've met the surprising exceptions. But what does this all mean for us in our daily lives? Well, let's see how this very nobility is put to work in some absolutely incredible ways.
And here is the beautiful irony of it all. The very property that makes them seem so aloof and unreactive, their inertness, is precisely what makes them so incredibly useful to us in technology, industry, and even medicine.
This is basically the noble gas resume. Their inertness makes them perfect protectors. Argon protects the delicate filament in a light bulb from burning out, while a mix with helium protects deep-sea divers from getting the bends. They also literally light up our world. Krypton lamps can cut through the densest fog at airports, and xenon gives us that brilliant, intense flash for high-speed photography. And what's really remarkable is that even radioactive radon is used in targeted therapies to fight cancer.
So, you see, they're not just the aloof aristocrats of chemistry after all. There are silent partners in the modern world, working everywhere from hospitals to city streets. Their story is just a perfect example of how a unique chemical property can be harnessed in the most amazing ways. It really makes you wonder, doesn't it? What other secrets are they still keeping?